in the 10 questions that you answered just now, okay, you would have noticed that there were a lot of questions that asked about how do you explain pressure in terms of kinetic theory of gas? How do you explain volume in terms of kinetic theory of gas? How do you explain temperature, okay, involved when it comes to kinetic theory of gas? So these are three very important things, and how you explain them. Okay, so that's number one, very important. And the other type of question I asked is the relationship between pressure and volume, which is the first thing that we studied. Okay, and this is called Boyle's law, lah. And we know that pressure and volume are inversely proportional. But okay, from the graph that we did last week, and only a handful of you handed in, which I'm like still waiting until now. I don't know why it's taking so long for you to hand in your homework. Let me see. Yeah, so far only uh, only 8 people have handed in their graphs. Okay, so I'm still waiting for the rest. So from the graphs, you will have noticed that if it is P against V, then you get an inversely proportional graph. But if it is P against 1 over V, then you get a directly proportional graph. Okay, you get a straight line that begins with 0. And Boyle's law is the only law that is special this way. If you saw the other two graphs, if you have already drawn the other two graphs, you would know that the other two graphs look very much the same, very similar actually. Okay, because they talk about a different thing altogether, okay, which we want to talk about today. So have this in mind, especially the explanation of pressure, volume, and temperature in terms of the kinetic theory of gas. Okay, because as I've said in the first part of this lesson, of this subtopic, I said that in order for us to understand the gas laws, we have to understand how the kinetic theory of gas explains pressure, volume, and temperature. So pressure is, the collision. Pressure is caused because of the collision of the walls, collision of the molecules in the walls. Volume of the gas is determined by the volume of the container. How big your container is how much volume your gas takes. Okay, and thirdly is the temperature. The kinetic energy of the molecules determines the temperature, explains why the temperature is high and temperature is low. And this third one, especially, we've actually covered this in specific heat capacity, where we say that the reason why the temperature is increasing is because the kinetic energy is increasing. So that is a part of the kinetic theory of gas. Okay, so let's go on to what we're supposed to be learning today. Okay, so yeah, okay, everyone, fun time is over. Let's go back to the real work. Okay, so if you have your modules with you, please turn with me to Charles' law. We're at activity 3, which I think is page 111 or something like that. Okay, so we're going to be looking at Charles' law today. Specifically, Charles' law, I will talk about the graphs that only 10 of you sent. Okay, but never mind. So I will talk about the graphs in a little while, but first let's talk about Charles' law. Okay, so the first law we learned was the law about Boyle's law, which, so just as a recap, Boyle's law relates P and V, okay, pressure and volume. Okay, but in Charles' law, we notice that the two things that are involved here are volume and temperature. Okay, so let's take a look at this. So diagram A shows gas molecules in a cylinder. Now, according to kinetic theory, why does the piston not fall down? Okay, so the piston doesn't fall down because it is supported by the air pressure in the cylinder. If there was no gas over here, although there's a weight over here, okay, the piston, this piston over here, ombo in English is called piston. Okay, so the piston would actually fall down because of gravity. Gravity will pull it down, and because of course the weight is also this one. But we find that if there is gas in here, okay, we find out that the piston will not fall down because it is being supported by the air pressure in the cylinder. Okay, the gas molecules over here exert a pressure, okay, on the piston. Okay, so because of that, it will support, okay, the weight that is pushing it down. Okay, but if you heat up the gas molecules, okay, so diagram B shows the gas in the cylinder is heated. So what happens to the temperature of the gas? Vion, can you answer this, please? What happens to the temperature of the gas? What do you think?
Increase.
Okay, very good. So the temperature increases. Remember, guys, what happens? Increase, decrease, unchanged. Getting bigger, getting smaller, no change. Okay, generally, generally, when questions that these are asked, okay, these are the type of answers we're looking for. So in case you don't know how to answer, you just tembak lah. It's one of these three lah. Okay, you have a 1 in 3 chance of getting this correct. Okay, but have that in mind. And again, that's the reason why I call some of you to answer, because this one, no need information one, no, you can, it's very logical lah, kan. What happens to the temperature of the gas when you put fire to it? Of course, the temperature will increase. Okay, right. Let's explain what happens to the kinetic energy of the gas molecules. Okay, what do you think happens? What happens to the kinetic energy of the gas molecules when you heat up? Okay, when you heat up the gas, the temperature of the gas increases. Okay, so let's talk about the kinetic energy of the gas molecules. Can I have Chen He for this, please?
Increases.
Okay, so the kinetic energy of the gas, okay, of the gas molecules will increase as the temperature increases. So they work both ways. Okay, when the temperature increases, the kinetic energy of the gas molecules is increasing. That's the reason why lah. Okay, the temperature increases. Now, the thing that must be kept constant, okay, the thing that must be kept constant is pressure. Okay, now bearing in mind once again that the gas laws, okay, are a relationship. If you remember the triangle that we drew the other day, the gas laws are a relationship between pressure, volume, and temperature. Okay, so in Boyle's law, okay, when we were looking at Boyle's law, we were looking at pressure and volume. So since pressure and volume are changing, if pressure increase, volume decrease. If pressure decrease, volume increase. That means the temperature, okay, is the constant. Okay, but now in Charles' law, okay, in Charles' law, let's use blue lah. Fine, green. In Charles' law, since we're talking about volume and temperature, therefore, this one must be constant. Okay, and that's the beauty of the gas laws. It's only between these three. Okay, pressure, volume, and temperature. If these two is relationship, this one is constant. If these two is relationship, this one is constant. Don't ask me to do the one with the middle finger. Okay, so have that in mind now when we're talking about the gas laws. Okay, so explain why the piston is pushed upward. Okay, so when we explain it, it will be like this. It will be because the volume of the gas increases. Okay, why is the piston being pushed upward? In order to have more volume of the gas. Okay, so what is the relationship, okay, between the volume and the temperature? Take a look at this. This one, when there is no fire, this is the volume. When there is fire, then this is the volume. So what is the relationship between volume and temperature? Bernardine?
The higher the temperature, the larger the volume of
Very good.
gas.
Okay. No need to because. Okay, no need to because. The bigger sorry, what is the word you use? The higher. Okay. So the higher the volume, the higher the temperature. Let's just stick to that. Okay. The bigger the volume, the bigger the temperature. If you read it the other way, also can. But in this case, okay, in this case, it is the temperature that changes first. Okay, it is the temperature that changes first. So in this case, it will be the bigger the temperature, okay, the bigger the volume. Okay, but Charles' law actually is a relationship between the two. It can be the volume change the temperature, or it can be the temperature change the volume. But in this case, okay, in this case that you see in this picture over here, it is the temperature that changes the volume. So since the temperature is the one that's changing the volume, we write the temperature first. Okay, so temperature increase, volume increase. Okay, but in but in Charles' law, Charles' law actually states that volume is directly proportional to temperature. There's an A missing here. Okay, volume is directly proportional with temperature. But as I said before, this one is Charles' law. Okay, it is the definition for Charles' law. But if you're talking about relationship, we stick to this, how we answer this. Okay, the bigger the temperature, the bigger the volume. Okay, so Charles' law, as I said just now, Boyle's law is PV and Charles' law is VT. Okay, the bigger the volume, the bigger the temperature. And that's why this triangle becomes very important. Okay, astaga, hold on. Okay, oh no, okay, fine. This triangle becomes very important because it shows us that if it is straight line like this, P and V is directly proportional. But V and T, one up, one down, bahkan, is inversely proportional, P and V. V and T is directly proportional. Okay, so directly proportional means if V increase, T increase. If T increase, V also increase. Okay, now this is not in your module, but you can screenshot this if you want now. But this is the explanation of what is happening. Okay, so in a fixed mass of gas at constant pressure, okay, constant pressure is Charles' law. The frequency of collisions between the gas molecules and the walls of the container is constant. But when you heat up the gas, the temperature of the gas increases. So when the temperature of the gas increases, the kinetic energy of the molecules will increase. You'll move a lot faster. And since it is moving a lot faster, they will collide with the walls more frequently and at a greater speed. Yeah, compared to if there is no temperature, right? If there's no fire, okay, then they will not collide so much. But if it is hotter and they're moving faster, they're going to collide more. And so they exert a larger pressure on the walls. Okay, and because of that, the molecules are able to push the piston so that the gas expands. This is the key word when you're talking about volume change. Okay, the gas is expanding. Okay, and so the faster molecules now move in a larger space. Okay, the pressure remains constant. Okay, so the idea for Charles' law, and this is probably the one that will be very confusing with the next law. We will not look into the next law today. We'll look at only Charles' law today. But the important thing about Charles' law is the pressure must be constant. So in order for the pressure to be constant, okay, the volume has to increase. Just like a balloon, just like a balloon. If let's say you blow air into the balloon, so the balloon is a certain size. But when you heat up the balloon, assuming that the balloon doesn't burn off, okay? Let's say you heat up the balloon, you increase the temperature of the gas in the balloon is going to expand because it is able to expand. Okay, it needs to expand in order to maintain the pressure. Okay, in order to maintain the pressure, it needs to expand. And so Charles' law works in this way, okay, where things are able to expand. Okay, but what if you have a container that cannot expand? For example, let's say you have a box Okay, box mana boleh mengembang bahkan. Okay fine. Let's say you have a tin, no, not a tin. Let's say you have a cement box a cement block. Okay, if you have a cement block, okay, and then you put the gas molecules, you put a gas or you put air inside the gas block, you close it, and then after that you heat up the gas in there. It's going to be very hard to expand. And so when it is very hard to expand, then there is a constant volume already. Okay, and because the volume is constant, the pressure has to increase. Okay, so Charles' law and the next law we're going to look at, which is pressure law on Wednesday, is very closely related. Both of these laws involve increase in temperature. Okay, but Charles' law states that when you increase the temperature, the volume must increase so that the pressure can remain the same. Okay, and pressure law will be something else. So have this in mind first when we talk about Charles' law. We increase the temperature so that the volume can increase, but the pressure remains constant. Okay? It can never be you increase the volume and also increase the pressure. It cannot be both at the same time. It's only one at a time. Okay, and of course at this beginning stage, this is the hardest thing to understand. Okay, this is the hardest thing to get past. Okay, so let's take it slow. If you want, you can take a screenshot of this. I don't know, for some reason or another, I can't seem to erase this. Lana. Okay, so yeah, you can take a screenshot of this in order to read it again and to see if you understand what's happening. Okay, most important thing, increase the temperature. Okay, the volume will increase in order to maintain the pressure. Okay, the pressure of the gas is the same. All right, now let's take a look at your experiment. Okay, so this is the experiment to determine the relationship between volume and temperature of a fixed mass of gas at constant pressure. Now take a look back at the Boyle's law experiment that we did. Okay, and based on that, write down what the inference is for this experiment, write down what the hypothesis is for this experiment, and write down what the variables are for this experiment. Use the Boyle's law experiment to help you to write the answers for this. Okay, I give you 2 minutes to do this. Do this now, please. Raman for the inference, Elvin for the hypothesis, and Steffi for the three variables.
Um, the bigger the temperature, the bigger the volume of the gas.
All right. The bigger the temperature, the bigger the volume of the gas. Thank you.
Volume depends on the temperature.
Volume depends on the temperature. All right, very good. Hold on now. Apabila botol dimasukkan dalam, when the bottle is placed in the beaker of water. Okay, very good. Volume depends on temperature. Steffi?
Temperature, volume, and
And
the pressure and the mass.
very good. Okay, pressure and mass. There are always two constant variables when it comes to the gas loss. And always the mass is one of them. Okay, pressure of gas and the mass of gas. Okay, so volume depends on temperature. All right, very good. So I hope that by doing this, okay, we besides learning about the law, we also build our skill in making inference, making hypotheses, identifying the variables. Okay, it is a very important skill. Okay, so I hope that the rest of you who I didn't choose to answer, please be active learners. Okay, because I'm not just giving lecture. No, I'm also teaching you skills, how to answer questions, what are the answering techniques. Okay, so that you don't have to go for all this seminar technique menjawab. No need. Just listen to me. Very important. Okay, so this is how the experiment looks like. Okay, and it is a pretty complicated experiment lah. Okay, so you have a thermometer over here, and you have a capillary tube. Okay, and you have this paraffin oil over here. There's a piece of oil that is stuck in this capillary tube. A capillary tube is like a glass straw lah. Okay, it's like a glass straw. So that means in the middle there's a hole, and that's why there's the paraffin oil is there lah. It's stuck in there. Okay, so what happens is, of course, when you heat up the water, the temperature of the water is going to increase. And since we already said that the volume is going to increase with the temperature, this paraffin oil is going to move upwards. Okay, it's going to move upwards. So that means, and please take note of this lah. Okay, please write this down at the star. Okay, the length, okay, of this one, the vertical column of trapped air, okay, the length of trapped air, okay, represents the volume of gas. Okay, so the length of the trapped air is a representation of the volume of gas. Okay, so the bigger the temperature, you're obviously going to get a bigger length of trapped air, which is what we saw the other day. So I gave you this one. So you see that the bigger the temperature, the bigger the length of the trapped air. So the paraffin oil, which I can't see over here, okay, we find that the length is going to get a lot larger. Originally it's 6.9 maybe. And then after that, it goes up and up and up and up. So it's about 8.2. Okay. And so now we come to the graphs. Now we come to the graphs that you drew. Okay. And I have quite a few interesting questions that I want to ask some of you. Okay. So there are 10 of you that handed in. Okay. So beyond Trevor, Rahman. One of the first few people that handed in was Wong and Joey. Okay. And when I see Wong and Joey, and this is kind of expected. Okay. I don't know why Wong is doing this, but okay, fine. So notice that different people have different scales. So Wong has chosen a Wong has chosen a very lazy scale, which is 50 and 100. But the graph is so big. How come you didn't do this in the book? Not enough space in the book. Okay, anyway, well, we find that when Wong drew this, sorry, can you see this? Oh, okay, fine. So when Wong drew this, and quite a number of you did this, it is actually a increasing linearly graph. Remember, I've only taught you 3 graphs so far, which is inversely proportional, the one that curve like that. Then the directly proportional must start from 0 and then increasing linearly. Okay, 第三个 lah. Okay, the third one is increasing linearly, which is this one lah. Okay, but and so we find that generally most people for all the graphs they do the same thing lah. Okay, so I want to draw your attention to who should I choose now? Okay, let's ask Trevor lah. Why is Trevor one purple, one green? Did you put a filter on this? Okay, so this is the Charles law graph. Trevor, can I ask you why did you extend the graph all the way to the back? I'm not saying it's wrong. I just want to know why you chose to do that. Because everybody else just like stuck halfway. They stop at the y-intercept. But you chose to expand it half to the back. Why? Oh, I don't know. Instincts. Wow. Okay. Let's why would you say instincts? Okay, what about Carlson? Carlson is the other person that also did this. Why did you oh no, not this. Okay. So why did you expand this all the way? Okay, everybody, I want you to learn from Carlson. Carlson, sorry. So this is a very hardworking scale. 20, 40, 60. The 50 and 100 is so lazy. Okay, 20, 40, 60, 80, 100 is a more hardworking scale. Okay, it's a little bit more mafan, I know. It's very troublesome, but it's definitely a better scale. Okay, because it makes your graph look bigger. Okay, your graph very tiny, very not nice to see one. Okay, Carlson, why do you extend this all the way until behind here? Wow.
Because the scale until negative 300, so draw until the end now.
Oh. Okay, don't scold me, Carlson. I just wanted to know. Carlson sounds so angry. Okay, scared until negative 300, so just draw until the end. Okay. So I thought this was very interesting lah. I thought that that everybody would be like Carlson and Trevor lah, since the scale is until negative 300 miles, so just draw to the end lah, kan? Why would they ask us to put the scale until negative 300, tapi kan itu graph tu contour betul, it's so tiny in the middle over here. Okay, so there is a reason why lah. Now, if you have your graphs with you, I would suggest that you put it in front of you right now lah. Okay, especially this one, just for today, just the L against temperature. Okay, the length of column of air against temperature. Okay, this is the graph that I want to highlight. Okay, secondly, guys, whenever you write this one, please always have the symbol and the unit. Okay, and the unit you follow from the table punya unit. Okay, so let's go back to the table. So the table unit, sorry, this is the problem with changing screens. And change screens means okay, always have the symbol and the unit. Okay, that's the very important thing. So in this case, you'll find that the symbol is theta for temperature and the unit is degrees Celsius. So when you write it in your graph, okay, you need to make sure it's theta and then slash degrees Celsius. You don't have to write the words. You don't have to write tidak perlu tulis perkataan itu if you don't want to. But if you want to do like Rahman, what we saw in Rahman's work just now, he wrote everything lah. Okay, length of vertical column L/cm also can, but ini yang saya highlight kan. This is what I want to see. Okay, this is a very basic skill of drawing graph. Okay, you don't draw graph and then after that the graph, the label is empty. No, the label is empty. What is this relationship? Is it a relationship between my age and my intelligence, or is it a relationship between my height and my intelligence? So the bigger the height, the bigger the intelligence. Is that it? so we don't know. Okay, so that's why the this one is there lah. Okay, sorry, short people don't be triggered. Okay, it's nothing to do. It's just a It's just a lame joke lah. Okay, so sorry, this is how the graph will look like. But yes, okay. Generally, okay, what we will do is we will extend this all the way to the back. Okay, but this is the case, but because this data behind here is what we call is not given lah. Okay, so what we have to do is we have to extrapolate. Okay, when we extrapolate now, we extend the graph yang sedia ada, okay, by theoretically, that's why these lines are dotted lines or dashed lines, because these are theoretical values. Okay, so theoretically, the pattern of the dots seems to be in a straight line. Okay, so theoretically, if you extrapolate, you extrapolate means you put extra lines lah. Okay, extra, all the way until here, you will reach a certain value over here. Okay, which we will talk about today. But first of all, let's talk about the relationship between this. What is the relationship between L and theta for this? Wong?
L is increasing linearly to theta.
Okay, L is increasing linearly to theta because it is not starting from 0. Okay, now, so the graph that you drew, okay, is like this lah. Okay, and then you do like this. So when you extrapolate, okay, once again, sorry, please extrapolate with dotted lines lah. Okay, it should be dotted lines, not straight lines like this. So when you extrapolate to a dotted line, okay, you will come all the way up to here. Okay, have your graph with you as you do this. Okay, so you extend your graph all the way here. Okay, now what I would like you to do is I would like you to write in your chat in the chat, okay, what is the value of this temperature that you got? Okay, it will be around the same value lah, but it will not be the exact same. So different people will have slightly different values. Okay, if your graph is the scale is very small, okay, then you have a more detailed value lah. If your scale is so big, then you will not have such a detailed value. But it doesn't matter. Okay, just extrapolate the graph. Okay, and then everyone, okay, put down your values in the chat box. How much is the temperature? Okay, when the L is equals to 0. This L equals to 0, right? What is the temperature over here? Temperature is negative. Write this down now. L equals to 0. Temperature is negative. How much degrees Celsius? Okay, and write it out in the chat section. Let me take a look at your answers and see. So people like Trevor, Meryl, Carlson, you already have the value, right? So just tell me the value in the chat, please. All right, so you will find, everybody, that when you expand the graph, you will get a value that is between negative 275 to negative 285, around that value. Okay, negative 275, actually it's negative 270 until negative 280, around that value. Okay, and so why is this very interesting for us? Okay, what does it mean that when L equals to 0? When L equals to 0, means there is no volume. Okay, there is no volume. Essentially, you have compressed the gas until there's no volume. Okay, until it's volumeless. Okay, and we find that the only temperature where it allows us to compress the gas until there is no more gas is a very, very, very small value, a very cold temperature. Okay, which is negative 200 and something, negative 270, negative 280 something, depending on your graph. And the value of this temperature is a very important value to us. Okay, let's take a look. So let's say if, sorry, what am I supposed to do? Hold on. Okay, so this value over here, okay, this value over here that you see, okay, is actually a very standard value, and we call this negative 273 degrees Celsius. So somebody, probably by the name of Charles, okay, probably by the name of Charles, did this experiment, and he also did like you, he did the experiment and he extrapolated. And he got a value of negative 273 degrees Celsius. Okay, which is what we call the lowest temperature ever known to man. Okay, the lowest temperature that we can achieve on this earth lah, okay, is about negative 273 degrees Celsius. Okay, so over here, volume increases linearly with temperature. Okay, but let's say I want to make this graph, okay, as a directly proportional graph. You know, so directly proportional graph, stay with me, people. Directly proportional graph must always start from 0, right? Okay, so let's say what if we move this axis, we move it to the back. Okay, this is what will happen. So if we move it to the back, we will get a directly proportional graph. Okay, take a look at the dark blue. Okay, but this one, in order for it to be directly proportional, this one must become 0. Baru dia boleh directly proportional bahkan. Okay, but if we change the negative 273 degrees Celsius to 0, we have to change the unit. We cannot use degrees Celsius already. Because how can negative 273 degrees Celsius equal to 0 degrees Celsius? Cannot. We have to use a totally different unit altogether. Okay, and so let's say we get rid of the increasingly linear, okay, the axis lah. Okay, we just maintain this one while we put the this one over here. So we have to change this negative 273 to become 0. And we have to change the unit as well. Some smart aleck figured this out. Okay, and so what happened was he plotted the graph of L, okay, but instead of using the unit of degrees Celsius, he changed it to 0 Kelvin. Okay, it is probably Kelvin. It is probably Kelvin lah. Okay, that said that, okay lah, since we don't want to use negative 273 and we want to change it to 0 so that it can become directly proportional. Okay, I will name the unit after my name. Okay, so we now measure temperature in Kelvin. Okay, and when that happens, okay, we have to change the relationship a bit. So we say that now the relationship is volume is directly proportional with absolute temperature. If you're talking about temperature, then you're talking about you're talking about you're talking about degrees Celsius. But when you're talking about absolute temperature, you're talking about temperature in the unit of Kelvin. Okay, and this is actually, interestingly enough, the SI unit for temperature. Okay, for Kelvin. Okay, and very specific to the gas laws. Okay, so in this law and in the next law that we're going to learn, these are the only two times where we have to use temperature in Kelvin. Okay, and so what this means for us, okay, what this means for us is that 0 Kelvin equals to negative 273 degrees Celsius. Okay, it is the same situation. Okay, it is a situation where there is no volume of gas, but the temperature value is different because of the unit is different. And so by using this relationship, we can change any value of the temperature to Kelvin. Okay, if 0 Kelvin is equals to negative 273 degrees Celsius, okay, what we can get is this one lah. So what is absolute zero temperature? So absolute zero temperature is the lowest possible temperature, that is negative 273 degrees Celsius, which is also known as 0 Kelvin. Now, again, when I say lowest possible temperature, means lowest possible temperature we can achieve on the surface of the Earth. Okay, there is no temperature that's lower than that. Of course, when you go into outer space, we're thinking about negative 1000, negative 500, much, much colder lah. Okay, but on Earth, okay, on Earth where we are with all the atmosphere and everything, the lowest possible temperature we can achieve is 0 Kelvin or negative 273 degrees Celsius. So the gas particles, theoretically, they stop. Okay, at negative 273 degrees Celsius, they are totally not moving at all. No kinetic energy, they are not vibrating, they're just frozen. They're literally and truly frozen. Okay, and have zero volume because they cannot move. Okay, as long as gas molecules can move, there will always be a certain volume, okay, because they can move around. But the moment they stop moving, okay, is where they have zero volume. Okay, so the temperature measured in Kelvin scale is called the absolute temperature, which is why in this one I said that when you write the definition for Charles' law, okay, you have to be very important. Charles' law states that volume is directly proportional to the absolute temperature. Okay, a lot of people make this mistake because they only remember, oh, okay, Charles' law is directly proportional, and then they just write temperature, which is wrong, you know. If you're using temperature in degrees Celsius, the volume is only increasing linearly. But when you talk about absolute temperature, where the unit is Kelvin, then the volume is directly proportional. Okay, so because of that, whenever you want to change degrees Celsius to Kelvin, you add 273. And when you want to change from Kelvin to degrees Celsius, you minus 273. Okay, this is a very important thing. Okay, you want to change from degrees Celsius to Kelvin, okay, you plus 273. When you want to change it back, you minus 273. Okay, so absolute zero is at negative 273 degrees Celsius or 0 K. Okay, ice point. Ice point or the freezing point for water is 0 degrees Celsius. What is 0 degrees Celsius in Kelvin? 273 or negative 273? Remember, changing daripada degree Celsius to Kelvin, kita tambah. Okay, so Trevor is correct. It's 273. Kita tambah. Okay, steam point. We have learned before that water boils at 100 degrees Celsius. So what is 100 degrees Celsius in Kelvin? Okay, it will be 373 kelvins. Okay. Okay, so Charles' law states that for a fixed mass of gas, the volume is directly proportional to its absolute temperature. Please underline the word absolute, because if you don't have the word absolute, okay, then the definition is wrong. Because Charles' law and the next law, which is pressure law, okay, works under the premise of absolute temperature, which is in Kelvin. Okay, we never use degrees Celsius for this formula. Okay, so the formula that relates Charles' law is V1 over T1 equals to V2 over T2. Okay, and then this temperature, okay, put an arrow or something over here. Make sure, okay, it's in Kelvin. Okay, because if you don't change it to Kelvin, your answers will be wrong. Okay, definitely. Okay, now let me recap again. Boyle's law. Okay, Boyle's law is P1 V1 equals to P2 V2. Okay, this is Charles' law. V1 volume 1 over T1 equals to V2 over T2. And you have to make sure that the T2 is in Kelvin. Okay, so for your homework today, I want you to submit this one, take a photo of this, okay, into the Telegram group. Okay, just this one, I'll just change the unit for me. Okay, this one I don't think we need to discuss. I think you can just change from degrees Celsius to Kelvin and from Kelvin to degrees Celsius. Okay, take a photo and send it to me in the Telegram group. Okay, and then, okay, to prepare for Wednesday's class so that we don't waste time, can you try to answer number 2 and number 3? Okay, it's just 2 questions that involve Charles' law. Okay, the formula is V1. The formula is this, V1 T1 equals to V2 T2. It's not homework. Number 2 and number 3 is not homework, but I want you to try it out so that on Wednesday, okay, we don't waste time. I don't waste time waiting for you to answer. Okay, so just give it a try and see if you can get the correct answer. We will discuss the questions on Wednesday. Okay, but for your today's homework is just this. Okay, take a photo of this and send it to me. Do it by today, please. Okay, and at the same time, the graphs that you drew, okay, the graphs that you drew, the 2 graphs, okay, the 2 graphs, what I would like you to do is to only hand in the picture of the, oh, sorry, not this. Sorry, it should be this. Share this tab instead. Okay, I only want you to hand in a photo of this graph, length of column of air, okay, and temperature. Okay, so what you do is you extend all the way to the behind over here and tell me what is the reading. It cannot be negative 273 because you don't have the scale for that. Okay, so whatever value that you got just now, for example, just now, what is it? Trevor got 285. Trevor got negative 285. Okay, so let's say this is Trevor's graph. Okay, so Trevor, all you need to do is just, since you have expanded this, okay, you just write down here, okay, put an arrow over here or something, and then write down there negative 285 degrees Celsius. Okay, and then hand this picture only, okay, into the Telegram group. So today there's two homework. The first one is fix the graph, put in the negative value of the temperature, and then the second one is change the unit from Kelvin to degrees Celsius. And from the degrees Celsius to Kelvin. Okay?